We're going to wrap up this unit by learning about something called percent yield. To talk about the word yield, we need to break it down actually into two main types of yield. One is theoretical yield and the other is actual yield. So when we talk about theoretical yield, that's the first part here. We kind of assume that every calculation that we've done so far up to this point involves production of a product where everything goes according to plan, right? So you generally can expect that when we take two reactants, mix it up, whatever amount of product comes out in the end, we expect it to occur ideally to where all the product that's supposed to be made will be made. Now, that's of course that, assuming that all the laws of physics go your own way and everything just is nice and peachy. We actually use the term for that amount of product, right? Specifically the amount of product, not anything else really. Some specific amount of product, assuming that your experiment goes according to plan, that's called our theoretical yield, right? Because theoretically, you would be able to yield, you'd be able to produce a certain substance in a certain quantity. The next thing, though, here in practice mentions that usually the amount that you can obtain, the amount that you can actually get, the amount that you can isolate, is usually less than the theoretical yield. Usually, what happens in this question of why is it that the actual amount you can obtain is often less than the theoretical yield, is because things happen, accidents happen, you might spill something, or just by nature of trying to collect something, you might not be able to get all of it out, or something gets stuck to some other object, and you can't really obtain that and use it to count towards your total. So the actual amount of yield, right, therefore, is known as the actual yield. And this is the amount of product from an attempted reaction. So theoretical yield is pretty much what you can assume comes from the stoichiometry calculations that you've done up to this point. The actual yield is generally something that's been provided to you based on your own work, or is something that you would be able to get from a problem. Speaking of which, how do we actually then quantify how well we did in problems? Is a lot of times the problems ask you about percentage yield. Percentage yield, as you can imagine, right, refers to yield, so again, how much is made. But then percentage refers to its kind of efficiency, how well you did. So if you look at this formula here, percentage yield, right, that's equal to the actual yield divided by the theoretical yield. And of course, times 100, depending on how proficient you are with that. You might need to include that every time. But basically, we're looking at percentages here. So this is, again, telling us how efficient we are. Ideally, we definitely want 100% yield. We would love to have 100% yield every time, because that way we know that whatever we put in, we can get out. But, again, nature sometimes has its own ways of operating, so sometimes we don't always get 100% yield. Generally speaking, calculations are typically performed in mass amounts. Unless they specifically say mole amounts, you always generally want to use mass amounts. And this is one of those things where, again, if you were asked this question in a prompt, you would simply be assuming that it would be in masses. So please make sure you keep that in mind. There usually won't be a lot of other prompting to help you know that you're supposed to use mass amounts in that context. So whenever you talk about yield, we generally expect it to be a mass amount. To give us this idea of how this works, this is going to be a really, really simplified version of what it is that you might be expected to do to get percentage yield. So let's take a look at this problem. This is actually an example problem that came from a previous slide earlier. So this prompt here starts off with the equation. It's balanced for you. You get the coefficients here, 4, 5, 4, 6. And then it tells you that 3.25 grams of NH3, they're going to react with 3.50 grams of O2. So each of these reactants are brought together to produce something new. And they're asking, what is the percent yield if 2.00 grams of NO were collected in your experiment? One of the nice things that's kind of included for this prompt anyway is that it says in an earlier slide, when I mentioned this a minute ago, that you'd actually worked this out already. In an earlier slide, you determined that you could potentially isolate 2.63 grams of NO. So let's kind of take a look at, again, what the problem's asking you. It's asking you for a percentage yield. So percent yield is that formula of actual over theoretical. So that's effectively what that formula boils down to. And of course, if you want to write it times 100%, you're welcome to it. I'm going to leave it off because I assume that you can go back and forth between decimal and percentages. But the idea here then is that we have to figure out what we have in this formula. We're being asked for the yield, right? We need to get that value. And then we got to see whether or not we're given actual and theoretical yields. Are we given a actual yield? Well, what is this 2.00 grams business? Yeah, well, that's the actual yield because that's telling you that you were able to collect. You were actually collected in your experiment 2.00 grams. So in terms of plugging numbers in, I know I have this value. Right? That has the amount of NO that was produced. But if you were actually to go through and look at this next line and see that you could potentially produce or could potentially isolate 2.63 grams, that's going to be your theoretical. Because that says that according to the given amounts of 3.25 grams and 3.50 grams of this, of those two reactants, if you took those two masses and according to perfect stoichiometry, assuming everything goes the way it's supposed to, you could theoretically produce 2.63 grams, and that's why that goes on the bottom of this formula. That's your theoretical yield. Do a little bit of math, pay attention to your significant figures, and you'll find that the percentage is going to end up being 76.0%. So that reaction, you were 76% efficient, right? Of course, our theoretical or our ideal goal would be 100%, but sometimes that's the best you can get. Some reactions, and no matter how hard you try, no matter if you have the best scientists working on it, sometimes they only make like 36%. And that's how it is sometimes. All right, let's go and put this in action from a fresh problem, brand new one, where we haven't done any of the pre-work already. This is a problem that is going to basically look like any other one and ask you a few questions. And we've discussed this before, is that sometimes the questions they ask you requires a lot more assumed work than what it might suggest. So let's go and break this problem down. For parts of this, I'm going to speed through the work, at least show you that the work part I think you can take care of as long as you're comfortable with the logic. And then we'll talk through the parts that you might need to be a little more careful about. So first of all, again, we have the balanced equation, C6H6. We have Cl2. You have this substance right here in HCl. And this substance, has a lot of, or these equations are a little bit wordy, so hopefully you'll be able to follow along. When 36.8 grams of benzene, right, so B-E-N-Z-E-N-E, benzene, C6H6, that's this substance right here, is reacted with an excess of chlorine. The actual yield of chlorobenzene is obtained by a chemist, or that is obtained by a chemist, is 38.8 grams. So based on the work, right, so we're saying that we have 36.8 grams of this. They're saying that there's an excess of chlorine. So they're saying that there's a lot of chlorine around. That's going to produce C6H6, or this product right here anyway, and then some amount of this. But the important thing is this focus right here. Right? So basically what they're saying then is that 38.8 grams, what that represents is your actual yield. Okay. Now, let's deal with the problem. Number one, what's the theoretical yield of chlorobenzene? All right, theoretical yield. So this language right here, what is the theoretical yield? The word yield in this case is referring to a mass amount of this product right here, C6H5Cl. And how do we figure that out? Well, again, according to the basics of stoichiometry, if I have some mass amount of benzene, I can figure out how much I'm supposed to get of chlorobenzene. That's the theoretical yield. You've been doing this problem over and over again. You've been doing this kind of work over and over again, just now we have an actual term for it, or a different term for it. So I'm going to go and pause here. I'm going to write out all the work that you're supposed to be able to do, and I think you'll find that it makes sense. So this is effectively what you have to do. You have the given amount right here. Your goal is to get the gram amount of C6H5, and so we apply the molar mass, we apply a mole ratio, we apply the molar mass again for the new substance, and you're supposed to get 53.0 grams of C6H5Cl. Really quick typo, this is actually supposed to read 53.0, but you get the idea. Now, that takes care of number one. What's the theoretical yield of chlorobenzene? It's supposed to theoretically produce 53.0 grams. Second question, what is the actual yield of chlorobenzene? In this case, right, this is actually already given to you. We've already addressed this. The actual yield is 38.8 grams because that's how much you were actually able to collect. It's not how much you were supposed to get. It's more of just what you got. Finally, number three, what's the percent yield of chlorobenzene? I really hope, again, that this is just an application of that percentage formula for most of us, so no problem here. Go ahead and take the 38.8 grams of product that you're able to obtain divided by the 53.0 grams that you were supposed to get, and that'll end up giving you a percentage, or probably a decimal, but converting it to a percentage, 73.2%. Alrighty, that'll do it.